Honors Chemistry, and welcome to Chapter 11, covering 11.1 through 11.7, which is an introduction to gases and an introduction to the change-based gas laws. So, just as if we were in class, go ahead and take notes in your outline and copy the problems, like all the same stuff as if we were in class, except I guess it just removes the added pressure of, you guys having to answer me in class. So anyway, kinetic molecular theory, make sure you know those 4 principles as listed in your guys' book, because those are going to be the foundation for all of your explanations. So know them, in other words, memorize them, right? And be sure that you can talk about them. When you're talking about them, make sure that you remember, right, principle number 1 comes with the constant straight line motion, right? Gas molecules are in constant straight line motion, which is important, right? Because that explains why they move across space, right? Number 2 talks about no attractions and no repulsions, right? If there are no attractions and no repulsions, that's important because that means that when they run into each other, they're not going to stick, right? Which means that all of their collisions are elastic, right? I think you might talk about that a little bit in middle school, but what that means is that there is no energy lost when they collide, right? And so elastic collisions. Your book also talks about how average kinetic energy is directly proportional to temperature in Kelvin, right? That's number 4, I believe. Average KE, and when we think about KE, what's that mean? Right, that's the energy of motion. So we're talking about the movements of these particles, right? Kinetic average, or kinetic energy, the average of that, right, is proportional to the temperature in Kelvin, must be in Kelvin. When we talk about gas laws, the temperature must always be in Kelvin. So make sure you know that, right? And then principle number 3 talks about the space between the particles, right? So if we're thinking about what that means, if this is one particle and this is another particle, them being very, very far apart means that the actual size of the particle is of little relevance, right? That's, for example, comparing this size to this size, right? That green size is so many orders bigger than the yellow size. That does the yellow size really matter, right? That's what number 3 is talking about. The volume of the particles are so small compared to the amount of empty space between them, right? And it's important that we know all of these principles because 1, like I said, they explain our change-based gas laws. 2, right, they help to explain the gas properties, right? We talked about in chapter 3, and your chapter 11 goes over it again, how, right, gases are compressible, gases have low densities, and gases take the shape and volume of any container, right? And all of those can be explained using principles of KMT, so make sure you can do that. Terms that describe gases include pressure, volume, temperature, and moles, yes? And so when we think about pressure, you should know that that is the P, right? Volume is V, temperature is T, always in Kelvin when we talk about gas laws, right? If you need a refresher on how to do your temperature-based conversions, that's back in chapter 3, right? And N is our moles, right? And you know how to convert 2 moles from mass, for example, right? You can get to moles from volume if you have a density and a molar mass, right? So don't forget that a problem doesn't have to directly give you moles. You can get to moles from many different things, right? And pressure, right? Your book goes over the different pressure conversions, so make sure that you know those so you can use them, right? And make sure that your pressures match in change-based gas laws, right? And you know all of your volume conversions, right? So that way you can make sure your volume units match across a conversion. Okay, next up, scenarios to consider, just things we should know and be able to discuss, right? So first of all, at increased elevation, right? So this is like, think if we're on top of a mountain or we're in Denver or some other mountain city, right? Is atmospheric pressure higher or lower than at sea level, right? So if we think about it, right, here's sea level and here we are at sea level, right? And then if we were to ascend a mountain, right, and be up here, right, what is the difference in the atmospheric pressure? Right, if we are down here, it's like having a giant column of air pressing down on us, right? Whereas if we are higher up, there is less column of air pressing down on us, right? So at higher elevation, atmospheric pressure is lower than at sea level, right? And that pressure discrepancy is what leads, for example, humans who live at sea level to feel funny when we go up to higher elevations, right? Some people will get like legitimately sick, right? Some people will just feel uncomfortable. And for most people, that'll usually pass after you acclimate, right? Okay, that's stuff we should know. And that also leads to differences. For example, if you've ever gone to higher elevations and noticed that your chip bags are all a little bit fat, right? Or if you've ever read your actual boxes for, say, baked goods or for any instant food, right? How it's got slightly different cooking instructions at higher elevations, right? Because of the fact that the atmospheric pressure is lower, which means that gases behave differently. Okay. Blowing into a balloon, what gas law or relationship is at work, right? As we blow into a balloon, right, what are we doing when we blow into the balloon? Right, we are increasing the moles, right? That's what we are doing, right? With every exhalation into the balloon, we are adding more gas molecules. So we are increasing the N. And what do we notice that happens? Right, the volume of the balloon gets bigger, right? Meaning that volume and moles have a direct relationship, which we should know because we've all probably had to blow up balloons for a birthday party before, right? Which then this is V1 over N1 equals V2 over N2, right? Assuming that T and P are constant, right? And that's the assumption. I can only compare two pieces of information if the other two pieces are constant, right? Going back over here, there are 4 pieces of information that we can use to describe our gases, right? I can compare any two if the other two are constant. In a balloon, because the volume is flexible, what that means is that the pressure is constant, yes? In a balloon, because it has a flexible volume, the pressure is constant, meaning the gas molecules inside are always going to equilibrate with the pressure that's outside. Yes, does that make sense, right? Which means that volume and moles are directly proportional. If the moles go up, volume goes up. If volume goes up, it's because moles went up, right? As long as T and P are constant, right? Now, Febreze, right? So if we look at this labeling here, right? Febreze has this warning about where does it say? Do not expose to heat or flames and do not store at high temperatures, right? And so why is that, right? Why can't we, go around throwing all the sealed jars into high heat, right? That's because pressure goes up as temperature goes up, as long as V and N are constant. Yes? So if we think about what that means, right? So in a like a Febreze canister or whatever else, right? Volume is fixed. Yes? That's how this scenario is different. When the volume is fixed, meaning the volume cannot change, then the pressure will change in response. Yes? Does that make sense, right? So here, volume is constant because the volume of this canister cannot change. Therefore, the pressure will change. Yes, like that's what makes these two relationships a little bit different, right? And so what this says is if I increase the temperature, I increase the pressure, or vice versa, right? If I put a balloon on ice, right, that means my temperature goes down and my volume is also going to go down. And this is assuming that P and N are constant. Yes, where what we're saying here is that if I increase the temperature, the volume will go up as long as the volume is flexible. If the volume is not flexible, the volume then the pressure is going to go up, right? So these two are like similar scenarios where we're changing the temperature, and whether it's pressure or volume that responds depends on what the scenario is, right? Is the container flexible or is the container rigid, right? Carbonated beverages, I assume we've all opened one before and heard what? Right, we've heard that fizzing sound that indicates gas is escaping from the vessel, right? So gas is escaping, gas is moving from that tiny little space above the liquid into the giant room that is available, right? Meaning that the volume is going up because we have changed the pressure, right? This is the only one that is different. And this is, if we're talking about P and V, that means N and T are constant, right? So if we think about opening a soda, right, what we're doing is we are allowing for a greater volume. Yes, we're increasing the volume accessible to the gas. And by doing so, we decrease the pressure. Yes, that's what we hear. That's why the gas all rushes out, because now it's got more space and it will go to that more space courtesy of that constant straight line motion that gases are always doing. Yes? All right. So what this means is that these are the gas laws that we actually use, right? So for example, here and here and here and here, these are relationships, right? That tell us, right? So in this case, when one is on top of the other, right? That means their quotient is constant, right? Which means that they're directly related, right? If their product is constant, that means they're inversely related, right? And so these are just math principles, and we can use any of these equations to explore, right? What happens if we change a thing, right? That's what the ones and twos imply, right? Ones are scenario one, twos are in the second scenario, and we can use these to solve for lots of things, right? Here are some practice, right? There are 3 here and 2 more on the next page. Go ahead and jot these down, and then we will solve them together. So pause and copy. All right, talking about how to solve them. It says a sealed container. If it is sealed, what does that imply? Right, sealed tells us that N is constant, right? Gas is not getting in or out, so that means I can cross N off of things to consider, right? It holds 12 mils, so this is a volume of air at sea level. What's that telling us? Right, that's telling us 1 atmosphere, right? So that's our P, right? And 270 Kelvin, so this is our T. It says if the container is flexible, why is that important? Right, meaning volume can change, right? So V2, what changes as the temperature is increased to 550, right? And this is our T2. Now, does it say anything about the elevation changing or the pressure changing? Nope. So this is just a volume and temperature relationship because P and N stay constant, yes? So then we just set up our problem, right? V1 is 12 milliliters over 270 Kelvin. And this is going to be equal to our new volume over 550 Kelvin. And then we just have to solve, yes? Then it's just, can you do the math? Note that here, right, so going back to KMT, temperature must always be in Kelvin. But the other things just need to match across the equal sign, yes? What that means, though, is I need to bear in mind that once I solve for this, what are the units of V2 going to be? Right, the units of V2 are going to be in milliliters, right? And if we do this right, we should get 24 milliliters as our volume. And then we would stop and reason through that. Okay, well, if I increase the temperature, does it make sense that the volume went up? Yes, it does, right? Because they're directly related. All right, next one says a sealed container. So sealed, again, means that N is constant. We don't have to worry about that. Holds 12 mils of air, so we got a volume. Sea level, this is 1 atmosphere. 270, this is our temperature. If the container is rigid, right, that means V is constant. What changes as the temperature is increased to 550? So that means we're looking for a P2, right, with my new T. So we're going to do 1 atmosphere. 1 atmosphere over 270 Kelvin is equal to P2 over 550 Kelvin, yes? And then we will solve for our P2. And if we do it right, we should get 2 atmospheres. Does it make sense that my pressure went up? Yes, it does make sense that the pressure went up because our temperature went up, right? In a rigid container, right, which meaning the volume cannot change, therefore the pressure will, yes? All right. 1 mole of gas, 1 mole, that's our N, occupies 22.4 liters. What volume, so here's my question, would 0.5 moles of gas occupy? Oh, well, This is one of those scenarios, kind of like a limiting reactant that we talked about, where if we don't know more information, we can assume that those stay constant, right? The problem doesn't reference pressure changing. It doesn't reference temperature changing, which means that we can limit our focus to just V and N, right? So we know that V1 over N1 equals V2 over N2. And then we just have to solve, yes? And for our V2, we're going to get 11 liters. Ooh, our volume went down. Does that make sense? Right, that's like letting half of the particles of gas out of our balloon, and it makes sense that if I let out half the particles of gas, I'm going to get a smaller volume, right? Okay, next up. 1 atmosphere of gas, pressure, has a volume of 10 liters at 200 Kelvin. At what temperature, here's our question, will the gas be at 203 kPa, which is pressure, and 5 liters, which is our volume, right? So as we look at this problem, what makes this problem different than some of the previous problems? Right, we now have 3 pieces of information that are changing, yes? Well, we have 3 pieces of information, and so we've got to consider all 3, right? Which means that we would use that combined gas law, right? Which says PV over T equals PV over T. Now, what else is different about this problem? Right, our pressure units don't match across the way, which means that we have to fix that problem before we start, or as we start. Which one you choose to change is up to you. It doesn't matter. They just need to match across the equal sign, right? So let's go ahead and set this up. We have P times V over T is equal to P, so 203 kPa, oh, kilopascals. And then here is where we think to ourselves, 101.325 kPa is equal to 1 atmosphere, right? And our new volume is 5 liters over T2, yes? All right. And then if you take a moment and solve for T2, note that here, this is probably one of the most common sources of error is when we're solving for something in the denominator. Because some of us, our first instinct will be, I will take 10 divided by 200, and then I'm just going to divide it by everything else. But remember that T2 is not the same as 1 over T2. Yes, those are inverses, and so that doesn't work. So don't just move everything without thinking about where is the thing you're looking for, right? If it's in the denominator, then you're still not done, right? You still need to bring that out of the denominator, right? So cross multiplication is something where if you're prone to making math mistakes, cross multiplication might be a good place to start. But once we solve this, we'll find that, we land at 200 Kelvin. And then we'd stop and think to ourselves, what? Does that make sense? And then you would say, of course it does, because all I did was, what did I do to my pressure? Right, we doubled the pressure, but halved the volume, which means we land at same temperature, yes? All right. Finally, it says a gas has a volume of this at that. What is the volume if the new pressure is that? We've got to do the pressure matching thing again, right? But this is what relationship? Right, PV equals PV. Because we were not given information about anything else, so we can just assume those things don't change, right? So starting with 500 mils times its pressure, which is 775. And again, what you switch, totally up to you. Millimeters of mercury is equal to new volume, so V2, times 28 inches of mercury. And then what do we got to do here? Right, we've got to get those inches of mercury to millimeters of mercury, right? How do we do that? So one, you can just use those relationships in your book, but also you already know the relationship, yeah? You know that 1 inch is equal to 2.54 centimeters, which would be 25.4 millimeters, right? And that's our relationship, right? That's how we get from there to there. And we could solve this, and we would get that V2 is equal to 540 milliliters. Yes, again, it's going to spit it out in whatever unit it was in over there. Yes? All right. So this is an introduction to change-based gas laws and gases, right? Note that in every single one of these problems, right, all of these and all of these, something is changing, yes? We're not talking about chemical reactions, right? We're just talking about changing something and then calculating how the gas responds to that change, yes? That's all we're doing for today. All right, go ahead and do these practice. And all right, that's all. Be good. Have a lovely day. Do these EOCs. Next chunk of chapter 11 is due, where we start to layer back in chemical reactions, right? So make sure you're good with this stuff. Bring any questions you have tomorrow. That's all. Be good. Have a lovely day. See you guys tomorrow.